In this video, we are going to study Fourier series. Let fx be a periodic function of period 2 pi, which can be represented in the interval c to c plus 2 pi and given by fx equals a0 plus summation an cos nx, n runs from 1 to infinity, plus summation bn sin nx is called Fourier series. Here it is assumed that this series is uniformly convergent, which means gives a finite value and can be integrated term by term in the given interval. After integrating both sides of this expression of fx from c to c plus 2 pi, we get these constants a0, an and bn, known as Fourier coefficients. Let us study all these things in detail. For this summation bn sin nx, here also n runs from 1 to infinity. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will appreciate my efforts. You can also explore the playlist of this channel. You might find some videos that you are looking for. Thank you. There is more to it. This periodic function fx with period 2 pi must satisfy certain conditions known as Dirichlet's conditions. According to Dirichlet's conditions, function fx defined in the interval c1 less than or equal to x less than or equal to c2 can be expressed as Fourier series under following conditions: a. fx and its integrals are finite in number and are single valued. b. fx has finite number of discontinuities. And c. fx has finite number of maxima and minima. Let us understand what is periodic function. If at equal intervals of abscissa x, that is x coordinate, the value of each f of x, that is y coordinate, repeats itself, that is f of x is f of x plus a for all values of x, then y equals fx is called a periodic function having period a. Sin x, cos x are periodic functions having a period 2 pi, because sin x equals sin of x plus 2 pi same as sin of x plus 4 pi, so on and so forth, having period 2 pi. Same is the case with cos x. Cos x is equal to cos x plus 2 pi equals cos x plus 4 pi, so on and so forth, having period 2 pi. They are also called sinusoidal periodic functions because their graphs are of the type: the first graph is of sine function and the second cos function. Here, at equal intervals of abscissa x, that is 2 pi, the value of each fx, that is y coordinate, repeats itself from 1 to minus 1. Hence, period of these two functions is 2 pi. The function whose graphical representation is shown here has discontinuities at 2 points x equals a and x equals b, because here limit of the function as x tends to a is not same as value of the function at x equals a. Same is here, limit of the function as x tends to b is not the same as value of the function at x equals b. Such functions may consist of a finite number of disjointed curves given by different equations. In another graph of a function, if x equals c is a point of finite discontinuity, both the limits of fx as x tends to c minus and limit fx as x tends to c plus both exist but not equal to f of c. The first function with finite discontinuities can be expressed as a Fourier series, but in the second case, at the point x equals c, Fourier series gives the value of fx at x equals c as the arithmetic mean of these two limits. F of c is half left hand limit fx as x tends to c minus plus right hand limit fx as x tends to c plus. The discontinuity can be understood. For the left hand limit, value of the function is fc1 here, and for right hand limit, the value of the function fc2 is here. Since they are not equal, the function is discontinuous. In the Fourier expansion, fx equals a0 plus summation an cos nx n runs from 1 to infinity plus summation bn sin nx n runs from 1 to infinity. We will see how to determine Fourier coefficients a0, an and bn, also known as Euler's formulae. For this, we will integrate this expression on both sides from c to c plus 2 pi. So integral from c to c plus 2 pi fx dx equals integral from c to c plus 2 pi of a0 dx plus integral c to c plus 2 pi of an cos nx dx plus integral from c to c plus 2 pi bn sin nx dx. Being a constant, integral of a0 with respect to x will be a0 x from c to c plus 2 pi plus an integral of cos nx with respect to x will be sin nx upon n from c to c plus 2 pi plus bn integral of sin nx with respect to x is minus cos nx upon n from c to c plus 2 pi, which is a0 times c plus 2 pi minus c plus an into 0 plus bn into 0. We will see why these two definite integrals work out to be 0 separately. So this will be, after cancelling this c, 2 pi a0, and that gives first Euler's formula a0 equals 1 upon this 2 pi integral from c to c plus 2 pi fx dx. Now we will see why these two definite integrals work out to be 0. So an sin nx upon n from c to c plus 2 pi plus bn minus cos nx upon n from c to c plus 2 pi will be an upon n sin cnx plus 2 pi nx minus sin cnx minus bn upon n into, similar to this, cos of cnx plus 2 pi nx minus cos cnx. This is an upon n. By factorization formula, this will be 2 cos c plus d upon 2, that is 2 cnx plus 2 pi nx upon 2 sin of cnx minus cnx will be 0. So this will be sin of 2 pi nx minus bn upon n into, again by factorization formula of cos c minus cos d, this will be minus 2 sin c plus d upon 2, that is 2 cnx plus 2 pi nx upon 2 sin cnx minus cnx is 0. So this is sin of 2 pi nx upon 2, which is an upon n into, since this sin of 2 pi nx upon 2 is 0, minus bn upon n into, here sin of 2 pi nx upon 2 is also 0, giving us 0 minus 0, 0. We have obtained Euler's formula for this Fourier coefficient A0 equals 1 upon 2 pi integral from c to c plus 2 pi fx dx. Next we will find Euler's formula for this Fourier coefficient a of n. For this we will multiply this Fourier series by cos nx and then integrate as usual. So this will become integral from c to c plus 2 pi fx cos nx dx equals a0 integral from c to c plus 2 pi cos nx dx plus integral from c to c plus 2 pi summation an cos nx into cos nx dx plus integral from c to c plus 2 pi summation bn sin nx into cos nx dx. Earlier we have seen a0 into this integral works out to be 0 plus this second integral summation an cos square nx dx plus this third integral summation bn sin nx cos nx dx, which is a0 into 0 0 plus an into value of this second integral is pi. We will see why is it pi later on, plus this third integral which is 0. We will see why this is 0. So this will be pi an, that gives second Fourier coefficient an equals 1 upon this pi integral from c to c plus 2 pi fx cos nx dx. Now we will solve this integral and see why it is an into pi. So integral from c to c plus 2 pi summation an cos square nx dx, which is integral an into, in place of cos square nx we write half into 1 plus cos 2 nx dx, which is integral an upon 2 plus integral an upon 2 cos 2 nx dx, which is an upon 2 into x from c to c plus 2 pi, plus we have already seen integral of cos 2 nx dx is 0 equals an upon 2 c plus 2 pi minus c. Cancelling this c, we get value of this integral after cancelling this 2 also, pi into an. Similarly, let us solve this second integral also and see whether it works out to be 0. So integral summation bn sin nx cos nx dx equals integral summation bn half into 2 sin nx cos nx dx, which is integral summation bn upon 2. By defactorization formula, we write this 2 sin nx cos nx as sin nx plus nx 2nx plus sin nx minus nx sin 0 dx, which is summation bn upon 2 into, we have already seen integral sin 2nx dx from c to c plus 2 pi is 0. Therefore, this second integral is also equal to 0. So in summary, Fourier coefficients or Euler's formulae are a0 is 1 upon 2 pi integral from c to c plus 2 pi fx dx. An is 1 upon pi integral from c to c plus 2 pi fx cos nx dx, and bn equals 1 upon pi integral from c to c plus 2 pi fx sin nx dx. This is all for today. We will discuss more about this in the next video. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Post your constructive comments to improve the quality of the videos. You can explore the playlist of this channel, Number Collage. Perhaps you might find some videos that you are looking for. I take your leave now, but do keep watching Number Collage. Thank you.